Now you're going to take up one more problem. Here, problem number 38. A round bar with stepped portion is subjected to the forces, which is as shown in the figure. Determine the magnitude of the force P such that net deformation in the bar does not exceed 1 mm. E for steel is 200 GPa and that of aluminium is 70 GPa, and big end diameter and small end diameter of the tapering bar are 40 mm and 12.5 mm respectively. So here we have a round tapering bar of aluminium having the big end diameter is 40 mm and the small end diameter is 12.5 mm. And then the load applied is 4P on this side and 2P on this side of length of 600 mm. And then you have a steel bar having 400 mm square of 2P on this side and P on this side of 700 mm length. And steel bar of 200 mm square having 500 mm length of P on this side and 3P on this side. So this is, but here the loads are not uniform. Since the loads are not uniform, and therefore at each section the member has to be in equilibrium condition. So we need to maintain this. So when you want to take up the aluminium bar, you have an aluminium bar here. Then you have to take the on the left hand side. If the load is acting toward the left side, it is tensile, so obviously it is positive. And on this side, the load is acting on this end. The load which is acting towards the right side is positive because it is tensile, and the load acting towards the left side will going to become negative. There are three forces which is acting on the right hand side. One is 2P to the left, 2P to the right, P to the left, and 3P to the right. So 2P minus P plus 3P. So that means 5P minus P, which will going to become 4P. So therefore, so the first body in equilibrium condition for the tapering bar, 4P on this side and 2P on this side. 4P on this side. So both will be in equilibrium condition. When we are taking to the second position, if you are taking for the steel bar, if you are considering, on the left hand side, we have 4P is acting towards the left and 2P is acting towards the right. So 4P minus 2P will going to give you 2P again to the left side, and then P is acting towards the left and 3P is acting towards the right. Minus P plus 3P, again it will going to be 2P acting towards the right side. So steel bar will also be now in equilibrium condition. When you are considering for the third one, which is having 200 mm square, so there are three forces which is acting towards the left side and one force is acting towards the right side. The right side, which is the one force which is acting, which is 3P. So obviously here also you must get 3P. Now let us see how you are going to get. 4P is acting towards the left side, is positive, so 4P, and 2P which is acting towards the right side, it is minus 2P. So 4P minus 2P will going to give you 2P. Again 2P which is acting towards the left and plus P is acting towards the left, which is also becomes 3P. So 3P and 3P will going to be get balanced, which is the equilibrium condition. So this is how you will be able to analyze this. And now to summarize this, so here the free body diagram of different segments which are shown, whatever I have explained which has been shown here. So that is 2P is acting towards the right, P is acting towards the left, and 3P is acting towards the right. On the right hand side of the first, so 2P minus P plus 3P is equal to 4P. So the first is in equilibrium condition. So the first tapering bar of aluminium is in equilibrium condition. Now when you go to the second one, so what happens? 4P is acting towards the left and 2P is acting towards the right. So 4P, since it is the left end, 4P which is acting towards the left side is the tensile. So obviously it should be positive. 2P which is acting towards the right side is on the left hand side. It is acting towards the right side means it is a compressive. So obviously minus 2P. So 4P minus 2P is equal to 2P. And similarly, P is acting towards the left side, which is compressive in nature for the right hand. And 3P which is acting towards the right side, which is tensile in nature for the right hand. So minus P plus 3P which is equal to 2P. So both were in equilibrium condition. So we have the steel bar of 400 mm square will also be in equilibrium condition. And similarly, when you are taking for the third one, what will going to be this? So we have 4P and then 2p and p. So 4p acting towards the left is positive on the left hand, and 2p to the right is negative. 4p minus 2p plus p. So that is 5p minus 2p, which is equal to 3p. So you're going to get 3p, which is acting towards the left side because of the positive. So 3p is acting toward the right side in the right hand. So both are in equilibrium condition. So by using this, so now we have seen all the three different segments are in equilibrium condition. Now we will come to apply the formulas. ES is equal to 200 GPa, which is 200 into 10 to the power of 3 Newton per mm square. Similarly, E of aluminium will be equal to 70 GPa, which is equal to 70 into 10 to the power of 3 Newton per mm square. Similarly, delta is equal to 1 mm. And then for equilibrium of the bar, loads acting toward the right side must be equal to the loads acting toward the left side. 2p plus 3p will be equal to 4p plus p, which is 5p is equal to 5p. Now the body is in total equilibrium condition. Now what is the extension of the segment 1, delta L1? Since all the different segments have got the same all the different segments has got the tensile force, so naturally it is going to be the extension. So since it is a tapering bar, 4 into P into L by pi into E into D1 into D2. So 4 into P1 into L1 divided by pi into EAL into D1 into D2. So substitute the values. 4 into 4P into 600 divided by pi into 70 into 10 to the power of 3 into 40 into 12.5. So on simplification, you will going to get it as 8.73 into 10 to the power of minus 5p. Similarly, extension of the segment 2, delta L2 will be equal to P2 into L2 by A2 into ES. So P2 you know, that is 2p into 700 divided by A2, which is 400 into 200 into 10 to the power of 3. On simplification, you will going to get it as 1.75 into 10 to the power of minus 5p. What is the extension of the segment 3, which is delta L3, which is equal to P3 into L3 by A3 into ES, again, which will be 3p into 500 divided by 200 into 200 into 10 to the power of 3. On simplification, you will going to get it as 3.75 into 10 to the power of minus 5p. So what will going to be the total extension? The total extension will be equal to sum of the individual extensions of segment 1, segment 2 and segment 3. So the net deformation in the bar delta L will be equal to delta L1 plus delta L2 plus delta L3. So we know that delta L is equal to 1 mm equals 8.73 into 10 to the power of minus 5 into P plus 1.75 into 10 to the power of minus 5 into P plus 3.75 into 10 to the power of minus 5 into P. So on simplification, you will going to get it as 1 is equal to 14.23 into 10 to the power of minus 5p. So here P is equal to 7027.4 Newton. So this is how you will be able to solve this problem. Now we have one more problem, a prismatic bar, problem number 39. A prismatic bar of ABCD, capital ABCD, is subjected to loads of P1, P2 and P3, which is as shown in the figure. The bar is made of cell with modulus of elasticity E is equal to 200 GPa and the cross-sectional area A is 225 mm square. Determine the deflection at the lower end of the bar due to applied load. So here the load, you have three different segments which you are considering. One is P1 is equal to 8, P2 is equal to 8 and P3 is equal to 32. So the reaction at all the support will be equal to minus 8 plus 32 kilonewton and it acts in the upward direction. Minus 8 plus 32 kilonewton and it acts in upward direction. So here, so the minus 8 is acting in the upward direction, 8 kilonewton is acting in the downward direction and 32 kilonewton acting in the downward direction. So acting to the downward direction will be positive, acting in the upward direction is negative. So it is compressive. So naturally, since it is 32 kilonewton, so the 32 kilonewton should act in the upward direction. So the free body diagram of the different segments which are shown in the figure. So the first segment, which is minus 8 plus 32, which will be equal to 32 kilonewton. And in the bottom direction also, which will be 32 kilonewton. So that is for 500 mm length of 225 mm square. the area is uniform cross-sectional area. When you are considering for the top portion, so 32 plus 8 will be equal to 40 kilonewton. And in the bottom also 8 plus 32, which will be 40 kilonewton. So 32 plus 8 is equal to 42 kilonewton, 40 kilonewton. Therefore, the second segment is also in equilibrium condition, having 225 mm square of 500 mm length, which is BC. Similarly, when you are considering this, minus 8 plus 8 plus 32, which is equal to 32 kilonewton. And in the bottom also, you're going to have the 32 kilonewton. So now all the segments are in equilibrium condition. Now, what will going to be the total deflection? The total deflection of the bar delta L will be equal to deflection of the segment AB plus deflection of segment BC plus deflection of segment CD. So when you're considering all are tensile, so delta L will be equal to delta LAB plus delta LBC plus delta LCD. What is delta LAB? P into L by A into E of AB plus P into L by A into E of BC plus P into L by A into E of CD. So delta L will be equal to, for the first one, 32 into 10 to the power of 3 into 500 divided by area is 225 into Young's modulus is 200 into 10 to the power of 3 plus 40 into 10 to the power of 3 into 500 divided by 225 into 200 into 10 to the power of 3 plus 32 into 10 to the power of 3 into 500 divided by 225 into 200 into 10 to the power of 3. So the first one on simplification, which will be equal to 1.1556. So that is the total deflection of delta L. So this is how you will be able to solve this problem. If you find this video is useful, then you please subscribe to my channel. Thank you.